Okay, so problem 8.3 is basically a system like this. We have a battery right here. We have a coaxial cylinder that kind of looks like that. With the lengths of A and B respectively. A and this thing is B. And the first part it asks us for is use Gauss's law to determine expression for the electric field at a distance r from the axis of the cylinder where A is less than r and B is greater than r. So just write Gauss's law right here. Fast E dot dA is going to equal to the charge enclosed over epsilon naught. So that's the general formula for Gauss's law. The way we're gonna the Gaussian surface we're gonna draw is a cylinder bed. And so once we've drawn the cylinder, we can make this and simplify it a little bit. The integral of E dot dA Q enclosed epsilon naught. The Q enclosed is given to us. It's Q. E is going to be constant because it's going to be coming out radially outward here. It's a constant E radially outward, so we can pull the E out. And the integral of dot dA is the same thing as A, which is 2 pi r L. These two are given to us in the problem. So putting all this together, we're trying to solve for E, so we're going to do E is equal to the Q enclosed, Q, over epsilon naught, over this dA is coming down here, 2 pi r L. And that is that is electric field at R. Okay. Next part. The next part says determine the potential difference or voltage. So the formula for voltage goes like E dr, and then all we have to do for this is plug in our E from part A and then evaluate. So okay. Now pull out all the constants. Everything in here is constant except for the r, and that's the thing we're evaluating to. So we're going to get V is equal to negative Q over 2 pi L epsilon naught. And then remember we have this r here and then we have a dr, so we got dr over r. And then finally we integrate. So we get Q 2 pi L epsilon naught. Integral of 1 over r is ln of r. So we have, and we just substitute B and A, ln of B minus ln of A. Okay, and that's our answer. Cleaning this up a little bit, a definition of logarithmic functions, if you're subtracting them, you can divide them, right? And what we're going to do is we're going to take this negative and put this in here. We're going to multiply every term negative, right? And instead of getting ln of b divided by a, we're going to get ln of a divided by b. So our final answer, really clean, is just going to be q over 2 pi L epsilon naught ln of a over b. And that's it for number B. Finally, okay, so for part C, determine the capacitance of the capacitor. The way we approach this is we use the definition for capacitance, which is Q over V. given Q, that's just Q. And now we just have to substitute the V we found in part B. So we're going to get Q over, remember this is the V from part B, Q over 2 pi L epsilon naught ln of A over B. The Q's are going to cancel out here, and just simplify, bring this up top, this stays on the bottom. We're going to get C is going to be 2 pi L epsilon naught over ln of A over B. I mean, C is going to equal that. So that is the capacitance of this system. So part D, basically, we insert dielectric, and that's going to change the capacitance of this. And here are the system of equations that define the changing capacitance. Alright, and then C2. So we basically have split it into two capacitors right here. And then these capacitors are in parallel, as seen in the circuit in your diagram. So we're just going to add C1 and C2, and the final answer is going to be 4/3 C0. And that's it.